This module describes the use of FilmQA Pro to analyze a starshot image, and a protocol for recording gantry, collimator, and couch starshots on radiochromic film is available on the filmqapro.com website. An important point in creating a starshot image on radiochromic film is to use a dose to the film of 100 to 200 centigrade for each exposed line. That should be sufficient to make a high contrast mark. For a gantry starshot using build-up blocks, tailor the monitor units delivered to achieve that aim. Collimator and couch starshots are typically made without a build-up layer on top of the film, so the monitor units will need to be increased to compensate for the lack of electron equilibrium. Open the FilmQA Pro application, and in the Case Management object at the bottom of the case tree in the Case Data Selector window, click Add New Case Object. Expand the pull-out menu and select MLC Starshot Physics QA, and then click the plus sign to expand the starshot object. An image may be loaded in two ways, either directly by scanning or by opening a saved file. In this example, you'll load a starshot image from one of the folders included in the FilmQA Pro installation package. Go to Program Files, /Ashland Advanced Materials, /FilmQA Pro, /Images, /Example EBT2 Starshot, and open the file starshot1mm.tif. A thumbnail image of a gantry starshot will appear in the Starshot Physics QA case object, and the full-size image will be shown in the image window. The next step is to use the fiducial management tool on the image window toolbar to highlight marks on the film indicating the central beam axis and the transverse axis of the linear accelerator. In this instance, pen marks were scribed close to the center of each edge of the film, and while the recognition of these marks could be automated, human pattern recognition is superior when, as often happens, a film has other identification marks as well as the fiducials. So it's quicker and more reliable for you to highlight the fiducial marks in the software before fitting them. You're going to click on the icon for fiducial tool management. It's the second from the top of the image window toolbar, and use the general fiducial point. Since the fiducial marks are near the centers of the side of the dose film, the software senses whether a particular point is fitted in a vertical or horizontal direction, but you could force a particular selection if you needed. Now point the cursor and click on each fiducial mark in turn. The highlight marks appear. The fiducial fitting will be done using the center of the highlight marks, not the marks scribed on the film. And for precise alignment, click on a highlight mark, hold down the Control key, and use the keyboard arrows to move the mark. With the fiducial marks highlighted, click on the line Tools Starshot Physics QA at the bottom of the Starshot case object. Immediately, two circular analysis paths are added to the image window, and the results, including, among others, the smallest circle encompassing all beam intersections and the offset from isocenter, appear in the Analysis tab of the Analysis window. Depending on the properties of the starshot image, the analysis could be refined in three ways. The first of these concerns the radius of the analysis circles, and in general the larger circle should extend almost to the end of the beam lines, but not past the fiducial marks. In the gantry starshot, the beam lines extend to the film edge, so the larger circle could be 15 centimeters or more. The smaller circle should be a quarter to half the diameter of the large circle. Smaller is generally better, but if the diameter is too small, the maxima along the circular path become less distinct as the dose of the film fills in the decreasing space between the beam lines. Right-click on the image in the image window and select Axes Type and choose the display units. Pixels is the default, but length is more familiar, and I'll use that in this example. Click Length, and choose millimeters or something else if you require. Then use the horizontal sliders at the bottom of the image window to adjust the radii of the analysis circles to about 88 and 44 millimeters respectively. That's approximately 250 and 125 pixels in this 72 dpi image. The second adjustment concerns the width of the analysis paths. Up to a point, wider analysis paths are better because the pixel noise is dampened by an averaging process. But for the larger analysis circle, the wider lines must not extend past the end of the beam lines, nor should they overlap the fiducial marks. For the smaller circle, the analysis line should not be so broad as to come close to the area where the beam lines come together. Path width of about 3.5 to 7 millimeters is ideal. That's approximately 10 to 20 pixels at scan resolution of 72 dpi. Adjust the path width with the vertical slider at the bottom of the image window. As the path width is adjusted, the value is displayed in the slider button. The third adjustment is the minimum angle between the beam lines. And in general, the error in determining the intersection of two lines is inversely proportional to the angle between them. So there's a benefit to restricting the analysis to lines crossing at oblique angles. The 10 beam lines in the gantry star shot are 18 degrees apart. Right-click the options icon. It's the one depicting meshed gears under the chart in the analysis window, and choose minimum angle between beams and set it to 20 degrees. This eliminates 10 out of 45 beam intersections from the analysis, but it improves the measurement from the remaining intersection points, and the radius of the minimum circle is reduced from 0.5 millimeter to 0.2 millimeters. Detailed explanation of the detection algorithms used in the analysis is beyond the scope of this tutorial. And while there are other factors working in the background, none will need adjustment if the Starshot protocol is followed, and the dose to film in each line is in the 100 to 200 centigrade range. For example, consider the search for response minima and maxima along the sections of the analysis paths. If the doses are too low, then pixel noise in the image could result in detection of false minima and maxima. So stick to the protocol and no changes will be needed to the default settings of any of the other parameters to compensate for pixel noise. Besides analysis, the analysis window has two other tabs. Click the Profile tab to display the profiles along the paths, as well as the locations of the intersection points. Use the Normalize function icon below the chart to toggle between absolute and relative response values. And to change the absolute response units, go to the main menu bar and under Data, choose Units, and then select the desired value. Right-click in the chart area and under Display Mode, select one of the options to display a table of profile response values. Grab the border of the frame and slide it to display the table more fully. You can right-click on the chart or the table to copy either to another application. Now click on the Report tab, and at the bottom of the window check the items required in the report. In this case, I'll choose all four: Analysis Path, Starshot Analysis, Starshot Image, and Analysis Table. Then click the Output icon and select how to format the report. In this case, I'll choose all four charts on the same page. To save the report layout as a template, or recall a saved report layout, click on the Report Options icon and choose accordingly. If changes to a report format or layout do not update, click the big red star icon in the report panel to force an update. Finally, print or save the report using the familiar icons. This concludes the tutorial, but to get help in scanner settings and film placement on the scanner, refer to the tutorial model on film scanning.